So the last tool we need in our limits toolbox before we are limits experts and we're prepared for the rest of the course is evaluating limits approaching infinity. Okay, so this works maybe how you would expect. One way I can investigate this is right by making a table. So x approaching infinity means x getting really, really big. So the way I can do this, right, is I can see what happens to this function. This, by the way, is just a line, right? As I plug in bigger and bigger numbers. 4 times 1 plus 1 is 5. 4 times 10 plus 1 is 41. And then I get 401, 4,001, 40,000. And if we think about this logically, this pattern will continue, right? As the numbers get bigger, I have a linear function. The graph looks like this. We even draw an arrow at the end to show it will go up forever, right? So this limit, as x approaches infinity, so does the function. So we'd say this limit is infinity. And we're going to use similar logic now with negative infinity. Okay. So this means x is getting very large, but negative, right? So I can plug in some numbers. I can make a table to investigate this result. It's exactly what you would expect, though, right? So I get -3, -39. Then the pattern is kind of similar to the last one, right? Okay. So as x gets very large in the negative direction, the function approaches negative infinity. Okay, so exactly what we expect. Linear functions are pretty easy. Others, you just have to check your thinking. So let's look at a couple more examples here. So we have 3x to the third, and we have x approaching infinity. Well, this is just going to be a really big positive number as we plug in bigger and bigger numbers, right? So this limit is also equal to infinity. Here, though, you have to think, what happens when we cube a negative number? So we're plugging in bigger and bigger and bigger negative numbers. Well, let's say I'm not sure, right? So one strategy I could use is I could go to my graphing calculator. So I could type in my function. I could look at the graph. Negative infinity on my number line for my x's is to the left all the way forever, right? So we want to know what happens to the y values as x goes all the way to the left. I can even zoom out a little bit just to double check. But notice my graph goes down forever. Okay, so as x approaches negative infinity, so does the limit of 3x to the third, negative infinity. But notice now, this one is going to be different. Because remember, -3 is negative. And what we're doing is essentially, this is bad notation, but I want you to think about what is happening. We're essentially multiplying -3 times negative infinity, or at least -3 times a very large, increasingly large negative number. Negative times a negative is still a positive. So in this case, my limit is equal to positive infinity. Okay, so you have to do a little bit of thinking about what is happening here, but it follows pretty clear logic. And when in doubt, you can graph. I can take a look at what's happening on my graph. So notice on the left end of my graph, I'll zoom in a little bit so you can see. When I put that negative in, my graph is going up forever at the end. Okay, so let's make a note here. So if you're not sure, you have a tool to help you, and that's your graphing calculator. X approaching positive infinity will be associated with the right side of the graph, and negative infinity is associated with the left side of the graph. You already knew that. Okay. So the main idea here, and this is true for all functions, is to find a limit at infinity. You're examining the behavior of the function as you make x really big. And you can do that using a table or using the graph, or just using your brain. Right? Now is a great time to make sure you have all the notes, and then we're going to move on to a little bit more complicated of examples as we do. Okay, so rational functions. So these are functions made of fractions with polynomials. And you're familiar with this because we studied horizontal asymptotes last year in pre-calc. And what this graph would look like, 1 over x, you can graph it using a graphing tool. It would look like this. So as x gets really large to the right and to the left, we approach
0, right? So that's the horizontal asymptote of the function is y equals 0. That's also the limit as x approaches infinity. Okay. The reason for that, right, is as x gets very large, we get smaller and smaller fractions. If you want, you can make a little table. So you can have x and 1 over x, and you can see even right away 1 over 1 is just 1, right? 1/2 is 0.5. 1/3 is 0.3. 1/4 is 0.25. So those numbers are getting smaller and smaller. This pattern is also true if we want the limit to negative infinity. We can look at the graph to see that. We're still approaching 0. Okay. When we have x's top and bottom, our work is a little bit more complicated, but it's the same idea as our horizontal asymptotes from pre-calc. And that principle was that the leading terms, so the highest powers of x, determine horizontal asymptotes. So as x gets really big, this 5 and this 3 in this example don't really matter a whole lot. It's like if Jeff Bezos passed a dollar bill on the ground, he probably wouldn't bother to pick it up, right? Because this term is so much larger, but that 5 is really not contributing much to the whole value. Okay, so it's fair only when taking limits to infinity to rewrite this problem, if you want, as just 2x over negative x. Okay, and then look what we can do here. X, and I'm left with just the limit as x goes to infinity of -2, which is just -2, right? So my limit is the ratio of these two coefficients because I have x and x. Let's look for leading terms in our next one. So notice we have -x to the 4th here, and then 4x to the bottom. Okay, so I can ignore my smaller powers on top and bottom. So ignore that. And then let's think about what's happening here. So we have x to the 4th growing very fast because it's a bigger exponent compared to plain old x, which is growing pretty slowly. So the top of my fraction is growing much faster than the bottom. So this limit is going to be approaching infinity, but we have a negative on top. So we're getting a very, very large negative number. So my limit is negative infinity. This becomes super clear if we simplify this fraction, right? So if we take an x out of the top and bottom, we're left with -3x to the 3rd over 4. And this clearly grows to negative infinity, right? Because the bottom is just a constant. In our main idea down here, we're going to codify this a little bit more. I want to think about this last example first, though. This is an interesting one. So we did not see this type of function. So we have a polynomial over e to the x. We didn't see this really in pre-calc. Remember, e to the x, or anything to the x. So for example, 5 to the x. These are exponential functions, and then grow really quickly, right? That's the thing we need to know, so we can say they grow fast. That's why growing exponentially means growing really quickly, right? So these grow much, much faster than any polynomial function. So if I have the bottom of my fraction getting really large compared to the top of my fraction, well, that's approaching 0, just like our first example here. Okay, so those are some examples. This main idea is sometimes called the principle of dominance, but these are our rules. So if you're somebody who likes to write down the rules, here they are. Okay, so a and b are exponents. So this says if a is less than b, in other words, b is bigger, we say the fraction is bottom heavy. So bottom heavy means something like x squared over x to the 3rd. So that means my bottom is growing much faster, the limit is 0. If a equals b, so my exponents are the same, then the limit is the ratio of their coefficients. And that's because my x's cancel. Because they're equal to 1, anything over itself is equal to 1. So for example, 2x to the 3rd over 3x to the 3rd gives you 2/3. And then my last example, a greater than b. It means the top is growing faster than the bottom. So we say the fraction is top heavy. And this is, we saw this earlier, the limit is either infinity or negative infinity. So you have to double check. The way you can do that if you're not sure is by plugging in a really large value and just checking the sign. And then the last thing we're going to add is, this will be rule 4, exponential functions always dominate. Okay, so for example, e to the x over x to the 1 million, we'll say 1,000 because I don't want to write that many zeros, approaches infinity because e to the x will always grow faster. So there are your limits to infinity.